In use case 1.7, SIRT presents the artificial intelligence it developed to attack 5G infrastructure and cause degradation of service quality, or total denial. The algorithm is a type of reinforcement learning that does not require training and verification data. It has the ability to adapt its policy based on the environment in which it operates, adjusting its approach as it interacts with and learns from the surrounding environment. The AI can target three different protocols: TCP, UDP, and SCTP. It can also select the number of threads, the requests, the time between requests, and whether to keep the session open or closed for each request. The AI has the ability to generate custom network packets, and autonomously decides, not only the type and structure of these packets, but also the quantity, with the aim of effectively fuzz the target services. The use of reinforcement learning for the first time in orchestrating denial-of-service attacks on 5G networks, coupled with its aforementioned capabilities, renders this tool one of its kind. It is distinguished, not only for its effectiveness in executing a denial of service, but also for the sophisticated strategies it employs, which are a result of its advanced learning and adaptive techniques. This innovation marks a significant advancement in the field, showcasing a novel application of reinforcement learning in network security contexts. Now, an end-to-end scenario will be presented, starting with the AI denial-of-service attack on the 5G core network, followed by showcasing the AI-based intrusion detection system developed by SIRT, which is designed to mitigate this attack. In the upper left part you can see the services of the 5G core. Directly from below, the network traffic between the attacker and the AMF is presented using the Wireshark. In the upper right terminal the AI attack script is executed. Before performing any attack, the AI scans the service for open ports. As we can see, it detected 2 open TCP ports. Now it continues with the UDP port scan. In the Wireshark window you can see the packets sent by the AI during the UDP scan. The scanning process is completed by finding open ports for the SCTP protocol. As can be seen from the terminal, 2 open ports were detected. The AI continues with the evaluation of the quality of services for all the open ports it found, before it launches any attack. Based on this evaluation, it develops the strategy of the attack that will follow, and this is why this step is very important. On the first round, the AI chose to attack the SCTP protocol by deploying 154 threads with 79 requests per thread. It also created custom packets of 4,500 bytes to fuzz the AMF service. On the second round, it chose once again to attack the SCTP, but this time deployed one thread using 352 requests and 4,600 bytes for the fuzzing. After the attacks, the AMF has completely collapsed. AMF's CPU consumption has a 0 value as it has become offline. Because of this, all clients will receive abort messages for every SCTP requests they made. The strategy organized by the AI turned out to be extremely sophisticated and effective. To mitigate this attack, and ensure system integrity, the artificial intelligence intrusion detection system of Sancus was deployed. First, the setup of the 5G experimental environment is presented. The Floodlight SDN controller is activated on the upper right terminal, while the SDN network is presented on the lower right window. On the far right, the TCP dump tool is used to capture the network packets that will be used as input for the intrusion detection system. After all this, the 5G core network is activated. Floodlight's GUI illustrates the SDN-based implementation, including the 5G components which are interconnected with SDN virtual switches. There are 9 containers available. 2 are operating user equipment, 1 functions as an evolved Node B, and the remaining are dedicated to running elements of the 5G core network. For testing the 5G network's connectivity, 2 user equipments were employed to ping Google's website. The first user equipment is located at the bottom left, while the second user equipment is positioned at the bottom right. As it seems, the 5G connection is fully functional. The intrusion detection system is operational and actively monitoring the network for any anomalies. It hasn't detected any malicious activity, as the network is currently only used by the 2 user equipments, but this is about to change. A malicious actor uses the ML-enhanced attack tool to cause a denial of service. It starts scanning for open TCP ports to evaluate its target. However, the intrusion detection system promptly detects this scanning activity, and within just 1.4 seconds, sends out a notification identifying the specific IP address as hostile. To mitigate the ongoing issue posed by AI DOS attack, SRTH utilized a Q-learning agent that has been trained with input data from the Sancus P2 security recommendation problem. Given the current situation, the Q-learning agent has recommended the deployment of Countermeasure C3 that blocks the attacker's IP as the most effective strategy to counteract this particular threat. Following the recommended actions, the attacker's IP address was blocked effectively, countering the attack. As a result, all incoming traffic originating from the attacker's IP is now being denied, ensuring the network's integrity and preventing further unauthorized access. There is also the possibility for enhanced visualization within the Sancus dashboard. As observed, the attack was not only detected, but also given its corresponding description. Clicking on this description, more details are displayed, such as the time it occurred, the protocols it may be using, the attacker's IP, the source, and the target port. By clicking the remediation box, the administrator has the possibility to apply the countermeasure proposed by the agent from Sancus P2 security recommendation problem. In this demo, SRTH presented an end-to-end scenario, in which the successful AI denial of service attack against the 5G core was carried out. Subsequently, it was detected by AI Intrusion Detection system, and the attacker's IP was blocked, as suggested by the Q-learning agent of the P2 security recommendation problem.